All right, let's fix this camera first as usual. All right, so differential equations. We are back after this test, and the first section we want to look at, I had to postpone, but we'll get into it now, is 4.6. But the section is called variation of parameters. So I just want to talk really quick. I'll write it up here, but I want to talk really quick on how it connects to what we just did before the test, what you guys kind of finished with this test, and then we'll kind of see how it connects to that, and then what's going to be different about these problems. But yes, 4.6, they call this variation of parameters. I'll be honest too, the other thing about this section is I'm going to teach you a very short version of this. This is actually a much more general procedure that, yeah, so basically we're only going to consider a few types of problems that this method can solve. More for not only time, so I keep saying because we have 5 weeks, but more for we're gonna do the much broader set of problems that it could solve. I'd really have to teach you to show you the mathematics behind it, but really teach you some of the theory behind it, and that's what we unfortunately don't have time for in this class. So if we had time, I could teach you more of the theory, and if this class was more about theory, I could teach you more of the theory behind it, and you can kind of see there's a broader class of problems it's applicable to, and I will at least mention that what it's applicable to. But we're going to focus on certain problems today because you'll see they're very much connected to what you just ended, the problems you just ended doing. So anyways, variation of parameters. So variation of parameters. So what we ended with, we were looking at second order or higher linear non-homogeneous differential equations. So remember we ended with basically differential equations where derivatives had just constants in front of them, not even just constant functions. I mean, constants are constant functions, but not even just constant functions, just constants in front of them. And the right side of the equation had some sort of usually pretty nice function there. So a trig function, exponential function, a log function, a polynomial, right? And so remember with that last section where we ended is we figured or we knew figured out that so for a non-homogeneous equation, you still solve it like a homogeneous equation. You still get the complementary, what they call the complementary solution. But then you would use the function type that you saw on the right side of the equation to make a guess at, to form the particular solution. And I kind of mentioned that, again, like I just mentioned now, so all of the problems that we looked at, the right side, the thing that made it non-homogeneous was usually a pretty standard polynomial, trig function, natural log, e function, exponential function. It was something that was pretty standard, and I would say relatively tame. So the purpose of variation of parameters, though, so where we want to get to is, well, what happens if that right side is not tame? We have a way to solve to solve those things. Actually, give me a second. I also want to differentiate this section. Well, you'll see this section leads into 4.7, but I do want to differentiate it a little from 4.7. So give me yeah, this. So what happens if that right side, the non-homogeneous? So today we're still looking at second order or higher linear non-homogeneous differential equations, but we're going to look at ones where the right side is a little less tame and a little more complex. And so the question is there a way to go about solving those? And the answer is yes. So this variation of parameters ends up being a way that we could solve second order or higher linear differential non-homogeneous differential equations. And so, and like I was just saying before this, it actually ends up solving a wide variety, and it even will help you solve, you'll kind of see, um, it helps you solve what I was trying to make sure before I turned on this video. It helps you solve nonlinear, linear, non-homogeneous differential equations where even the constants, the coefficients in front of your derivatives are not constants. I think we mentioned this actually with the earlier section. So technically we could have, you can do that with earlier methods, but it's really hard. So variation of parameters ends up being actually a pretty darn general method for solving any second order. Well, and you can solve first order if you want to, but it makes it more complicated than not. But it ends up being a very general method, or pretty darn general method for solving second order or higher near non-homogeneous equations, even when the coefficients aren't constants. However, for the sake, like I said, for the sake of us not having the time to really develop the theory and like kind of see how it applies to this broader context, we are still going to look at differential equations. So the couple that we're going to do on this video are still going to be differential equations with constant coefficients. When we get to Cauchy-Euler equations, the next section, we will start to broaden and look at cases where the functions or the coefficients in front of your derivatives are not just constants. Anyways, but for today, I guess, let me write an equation up here. Actually, I'll actually start with something that at least looks as simple as, so this is number one in the exercises. Y prime plus Y. I'm sorry. Second, let me see if I want to change this just to, I probably shouldn't change it. Y double prime plus Y equals secant X. This is a second order non-homogeneous linear differential equation. And like I said, we're still just going to look at constant coefficients today. Again, it's not that variation of parameters can't deal with non-constant coefficients. It's that unfortunately we just don't have the time to do that, because that's one of those things that to do it, I couldn't shortcut it. I really would need to teach you a lot of the math behind this. So anyways, theory behind it. So something like this. But I do want you to see, so first of all, looking at this, does this kind of look like the last thing we did in what was it, 4.4? Hopefully you see, yeah, definitely. In fact, it doesn't look that too complex or really much different than what we did in 4.4. The kicker here is going to be the secant X. So the secant X, so again, in 4.4, we said if it was a natural log or an exponential or a polynomial or a sine or a cosine, we could do something with it. But even just the secants actually ends up being too complex for that method we learned in 4.4. So even just for a secant, we need something new to do with this. So again, I want to show you this, or we'll just kind of work this in a couple parts. Since variation of parameters, though, is a method you're using still on second order or higher linear non-homogeneous equations. When we did those equations, the first part was to find the complementary solution. The second part was to find the particular solution. Variation of parameters doesn't change how to find your complementary solution. In fact, nothing changes that. So if you think about that, again, the complementary solution is the solution when this equals 0. So even with variation of parameters, we're still going to find a complementary solution, because whatever my particular solution is, if I add the complementary solution to it, send it through this double derivative plus Y, I'm still going to get secant X. So whatever the particular solution is for this is what gives me secant X. And the complementary solution gives me 0. Secant x plus 0 is secant x. So you're still, again, this is why I kind of like this section is really a continuation of 4.4. You are still doing your complementary solution. In fact, in the next section, Cauchy-Euler equations, etc., the section after that, you're still always doing the complementary solution. And that's why 4.3 was such an important section, is that is how you get the complementary solution. So you're still always doing the complementary solution. What variation parameters changes, like I said, is when this non-homogeneous part is too complex to deal with, using the way we did in 4.4, it gives us, so it's gonna change the second part to this problem. First part is the same, complementary solution is the same, complementary solution is always the same. The second part is gonna be different. Figuring out how a particular solution where y double prime plus y equals secant x, that's what we're gonna have to do different this time. So all that to say, let's start with our complementary solution first. So let's start with y double prime plus y equals 0, and let's figure out what that is. So again, since you guys have done this quite a bit, go ahead and pause on your side. I'll pause on my side. Go ahead and get the complementary solution for that. All right, so for this part, easy enough. And so from this point on, especially, like I said, we're this complementary parts of the solutions is part of everything now. Every problem we do. I'm just gonna go ahead and write the, what do they call it? What is it? I think auxiliary equation. I'm just gonna go ahead and write polynomial we're gonna get from this that we're setting equal to 0. So this is, let's make this a lot easier. So this will be m squared plus m equals 0. And when you solve this, basically this is gonna be m equals I, m equals negative I. That means our complementary solution C1. So remember when it's what do you call it? When it's words, complex numbers. When it's complex numbers, then it turns into your solutions turn to that form e to the alpha. So if like your complex number is alpha plus beta I plus or minus beta I, your solutions turn into e to the alpha cosine beta plus what it's I think it's I sine. Crap. I'm forgetting the mode on it or the solution mode on it. Second. I think it's just sine beta. Yeah, I think it's just cosine beta sine beta x. Check. Okay, yeah, my last guess, my last meanderings was correct, so, so this is gonna be C1 cosine of 1x, so just cosine of x. C2 sine of 1x, because that's 1i. So that'll be our complementary solution right there. Again, I'm just gonna shorten up this process just because you know this, you guys know how to do this and you know it really well now. You can still play it all out on your own if, as much as you need to, but to save us time and space on the board, kind of doing these problems. All right, so then, so like I said, we're always gonna have a complementary solution, so we're gonna start there. But like I said, variation of parameters changes how I get this particular solution. And let me show you how that's gonna be. All right, so for the particular solution. So again, on the last sort of, again, the last section, what we did with the particular solution, kind of like we did for the complementary solution, is we sort of looked at this function and said, okay, this function, this type of function must be the answer. Again, like I was saying before, that works great on sine and cosine. We saw, you know, kind of when you take the derivatives of sine and cosines, you get a circle of sine and cosines. That works great on exponential functions because derivatives give you exponential functions. That works great on polynomials because derivatives give you polynomials, a different order polynomial, but nonetheless, or different degree polynomial, but nonetheless, they give you a polynomial. But if you think about it, for instance, secant x, what's the derivative of secant x? It's secant tangent. Or something like tangent, the derivative of tangent is secant squared. So the thing is, there's a lot of functions where the derivative of it introduces some other function into the system that it ultimately we're not seeing over here. So this is why I kind of pause for a second. I want to make sure, again, to give you guys a connection, since we can't do the theory behind it and really see some of the equations, I wanted to give you guys some sort of connection on why, unfortunately, we can't, you're going to see we're actually going to have to do something different than we did before, like a different strategy. Again, before we were assuming we saw this and we said, hey, then my original y must be something like this. But once it's not one of those nice functions, so if it's a, yeah, anyways, you know, if it's not a sine and cosine, it's not an exponential function or polynomial. We chose those, we used those almost more trial and error just because we knew their derivatives would come out nicely and kind of would give us the same type of functions, right? But with a whole other variety of functions that you guys know from your calculus sequence, that actually is not true. Derivatives end up wildly different. And then even worse, compound on that. So right now we're looking at a very simple example for this section, but let's say this was like secant x times, I don't know, so let's say it was secant x times tangent x, or let's say it was secant x times the square root. When you take the derivatives of those, of a function like that, you have to use the product rule, and then you're just gonna end up not just with wildly different stuff, but wildly different stuff that has a bunch of other pieces that we're in no way seeing here, right? So I say all that to try to convince you or try to get you to connect and see why once this for the non-homogeneous part of this equation, this is not a nice function, or even worse, it's some sort of complicated product or quotient of functions, then we can't use the strategy we did in 4.4 for the particular solution, which is guess the general form of this, take the derivatives and do your work from there, right? So we can't do that now, unfortunately. So what we end up doing for something like secant x, like, so again, like I said, something like secant x or literally some other function whose derivatives are not just copies of itself, essentially, or copies of its own type. Or what we do for something like this, where it is a product or quotient of functions that that's going to end up with a bunch of complicated pieces that we don't see on the right side. So what you do in that case is instead of assuming your particular solution is just some generalized version of the right side, what we assume is that, so let me kind of diagram this out a little. What we assume is that the particular solution is the complementary solution with functions stuck in front of these pieces. And so we're going to drop the constants. You saw again on the last section, your particular solution didn't have, didn't have a random, well, it sort of does end up having a random constant, but it didn't have a random constant. So we're going to drop these constants, but what we're going to assume instead is that our particular solution is these two. So basically this form, cosine x plus sine x, but we're going to stick some function in front of first one along with a second function in front of the second. And again, if we had time to kind of go over the theory behind this, so this idea of assuming your solution is in some sense a weirdly generalized version of the complementary solution where it is not just constants generalized, but what we're saying is our particular solution be qualitatively different from the complementary solution. The only way I can make it act different besides constants, right, is to actually multiply each of these pieces by a function. So cosine x is going to be multiplied by some other function, and sine x is going to be multiplied by some other function. It's kind of like kind of similar to when we did do section 4.3 and we're looking at the the complementary solution, the solution to the homogeneous equation. We have those examples where you would get the same repeated solution, and when you did that, let's say it was e to the 2x, but we needed two parts to our complementary solution, or again, two parts to our solution to the homogeneous equation. One of the solutions was e to the 2x, but that was a repeated solution. Then the next one would be x times e to the 2x. See, maybe you guys remember that, or hopefully that kind of rings a bell for you. So the second solution had to be kind of the first solution, but with not a constant, but with an actual function multiplied it. And so we took a shortcut that, again, I couldn't show you the mathematics behind, but the shortcut is just multiplied by x, right? So in some sense, what we're doing here is it's sort of the same idea. It's generalizing the same mathematical idea behind it, but we're generalizing that. We're not saying it's definitely x times cosine x or x times sine x. We're saying it is some other function times cosine x and some other function times sine x. And those functions could be a wide variety of things. So that's kind of the interesting thing here. So again, I know I keep repeating myself. I guess again, this is what happens when I don't have students here to have that feedback. So I can tell that the light's going on for you guys. But again, when you have second order higher linear non-homogeneous equation, and that non-homogeneous part is not just some simple, some relatively nice function whose derivatives all end up being the same type, or it's some complicated product or portion of functions. Then once you find the complementary solution for your particular solution, your assumption for a particular solution is wholly different. Your particular solution is not going to be a variation of this. The particular solution in this case is actually going to be a variation of your complementary solution. It's going to be the pieces of your complementary solution, each one multiplied by its own general function that we're then going to have to figure out a method to find. So that is what we're going to do from here is in fact, yeah, let me write this here. I guess I just wrote it here. We have got to go through some work. Basically, our job is to find u1 and u2. We got to find what functions are in front of our cosine and sine. Give me a second. Yeah. So that will be the rest of this is, we've got to do something. We've got to have some tool or some method find U1 and U2. So I could honestly just write, well, let's write of X just to emphasize that it is actually a function, not just constant. And I've got to write X over there. Okay. Of X plus U2. Sine of X. Okay. All right, so then the big question is, how do we find these? And so what I'm gonna show you, the way we find these, the interesting thing about this, again, huge lead in, but the interesting thing about this is we're actually gonna start to use, the way we find this, we're gonna start to use, sorry, we're gonna start to use matrices. And you wouldn't expect that to come up. There's nothing about, at least what I see here, that suggests that matrices would be a tool in any way for our solutions. And surprisingly they are. And again, I had the time to show you the mathematics. I could at least show you so you end up with a system of equations. And because of the system of equations, as you guys have seen in algebra before, you can recode it as a matrix. In this case, then see some work with that matrix actually gets us the solutions we're looking for. And it's because the math behind this, behind making this substitution and working this through, the math behind this gives you a system of equations. So what I want to also kind of seed forward for you guys or foreshadow for you guys is the interesting thing about this back half of the class, except for one part, but is it's not just this section, this method, variation parameters, where matrices pop up. You're going to keep seeing matrices actually pop up. We're going to keep getting systems of equations and finding that then matrices end up being a useful method for solving differential equations. And that's kind of a crazy connection. Again, at least algebraically, maybe it makes sense. You have systems of equations. You could recode it as a matrix and use it. But outside of that, I want you to just kind of think about how crazy we have these differential equations, which are derivatives of functions, and then somehow it ends up that this completely different mathematical object, matrices, end up being really useful for solving a wide variety of differential equations. I just want to let you kind of let that sit in your head. You don't even have to, you don't have to figure it out. Just let it kind of permeate in your head. Yeah, like yeast spreading in dough for the second half of this class. Because that does end up being true, and it's crazy. It's kind of weird. Anyways, so a bunch of lead up. How are we going to solve for U1 and U2? The first thing is you have to form what's called the Wronxian. So I'm going to give Wronxian. And then we're gonna start with what's called the Wronxian, and then I'll give you there's a W1 and a W2. But the Wronxian of the actually complementary solution. So the way the Wronxian works is you're gonna take and let me make sure I get this right. Let me make sure we include the constants or no. All right. So for the Wronxian, so what I'm going to do here is I'm going to write a 2x2 matrix that involves these two general solutions that you got for the complementary. There are these two parts of the complementary solution. So again, I'm not gonna use the constants, but I'm saying complementary solution. I basically got two parts to it: cosine x and a sine x. Cosine x and sine x. And then what you're gonna do, so the first row of your matrix is gonna be two parts to your complementary solution. The second row to your matrix is gonna be the derivatives of these. So what's the derivative of cosine? That's gonna be negative sine. And what's the derivative of sine? It's gonna be cosine. Now, normally the way we write matrices, right? So basically I'm gonna form this 2 by 2 matrix. The first row is the two parts to your complementary solution. Second row is your derivatives of those two parts. Then what I'm gonna do is I'm gonna find the determinant of this 2 by 2 matrix. If you guys remember, the determinant means you do multiply through on this diagonal. So you do cosine, you could do A times D minus B times C, or you do cosine times cosine down that diagonal minus result of sine times negative sine. That's cosine squared x, cosine times cosine, minus what's sine x times negative sine x? That's negative sine squared minus a negative sine squared makes it sine squared x. And if you can't do anything with this, you just leave it so, but this is my Wronxian. Now it does happen, you do know something about cosine squared plus sine squared. What is cosine squared plus sine squared always? But we know from pre-cal that that always equals 1. So in this case, my Wronxian happens to equal. Now, we're also going to form, two other 2 by 2 matrices, and we're going to again find the determinants of those matrices. So the first, so W1 is going to be the Wronxian. But so a good connection is they put a 1 here. What you're going to do is take the first column and you're going to replace it with a 0 up here, and then down here you're going to put what's on the right side of your non-homogeneous equation. This is where sort of this part finally comes in. So I'm going to place this first column with 0 on top and secant x on the bottom. Whatever's on the right side of your non-homogeneous equation. But then I'm going to keep the second column, sine x, cosine x. And then you're going to do the determinant of this. So the determinant of this now is going to be 0 times cosine x. What is that? That's a big fat 0. Minus sine x times secant x. What is minus sine x times secant x? Now, again, let's use a little bit of stuff that you know from pre-cal. Secant x you can write as 1 over cosine. So sine x times secant x times 1 over cosine. What does that simplify to, or how could you rewrite that? That's going to be tangent x. Sine over cosine is tangent. Negative tangent x, sorry. Negative tangent x. All right, so let's hold on to that. So I want to hold on, kind of highlight these pieces and hold on to them. So then W2, so again, W1, you took the first column and replaced it with 0 and then secant x. What do you think W2 is going to be? So very similar, where now we're going to go back and take the Wronxian, but now the second column you're going to replace with 0 and secant. So cosine, sine, negative sine. Really don't need the x's there, but at least you guys kind of understand what those functions are, so I don't need to see them. Cosine, negative sine. Let's do this right. Replace the second column with 0 and then secant x. And then we're going to go through and again do the determinant of this. So it's going to be cosine times secant minus 0 times negative sign, which is 0. And cosine times secant, what does that simplify to? Good, so like we just talked about, secant is 1 over cosine, cosine over cosine is 1. Is also 1. Alright. So I've introduced, so I'm saying, how do we find, the rest of this is finding U1 and U2. The question is, how do we find U1 and U2? And so I introduced this thing called the Ronxian, and it uses the parts from the complementary solution. You do a determinant, then W1 and W2 are basically the Ronxian with one of their columns replaced, 0, and then the piece from the right side of your non-homogeneous equation. And so you do your determinants, you get all this. Then the question is still, okay, that's great, but what is that for? So it ends up then that U1 prime, so not U1, but U1 prime is equal to, I'll make sure I get this right, W1 over W. And U2 prime, also a great band, W2 over W. W2 over W. Yeah, I'm pretty darn sure. I'm just making sure I don't have this upside down. Yeah. So that's kind of the connection and kind of the kicker here. So we're still gonna have to work our way to U1 and U2, but that's really the connection is you form all these because it ends up that U1 prime is W1 divided by W. It's the results you got for the determinants. And U2 prime is W2 divided by W. So U1 prime is negative. Wait, did I get the sign wrong? I swear, I feel like I got the sign wrong. So U1 prime is then negative tan x divided by 1, but we know that that's just negative tan x. And then W2, U2 prime is 1 divided by 1, which is just 1. Right now, these, again, the first problem in the exercises, so these are going to tend to come out with some nice simple things. Then now that you know U1 prime and U2 prime, how do you think you can figure out U1 and U2 from there? Good. So once you have these, notice that, I mean, you know the derivative. So we're saying whatever U1 is, this is the derivative, and whatever U2 is, this is the derivative. So we can just take the integral of them. Actually, kind of similar to the problems in chapter 2 where figure out the integrating factor, right? Or like exact equations, kind of like exact equations, kind of like the integrating factor equations, or the methods with the integrating factor in chapter 2 where your one side of your equation suddenly became the derivative of the thing you were looking for. So you just integrated to find the thing you were looking for, right? So in some sense, we're doing something very similar here. Some of the mathematics behind this is actually similar to the mathematics behind how the methods, the first order equations that required integrating factors and the exact equations. So that's actually why it does kind of, you end up with, again, not similar letters or anything, not, these don't look similar to what we saw in chapter 2, but the overall pattern for the way you go through solving it is similar, where you come up with sort of these pieces that we realize are the derivatives of the things we're looking for. So we just integrate our way back up to what we're looking for. Anyways, so that means I can take U1 is going to be the integral of negative tan x dx, and 2 is going to be the integral of now 1 dx, which is dx. And we can do those integrals pretty easy from there. So I want to give you guys a second to do those integrals. Actually, yeah, so go ahead and pause on your side just a second. It shouldn't probably take you too long. So go ahead and pause on your side, I'll pause on my side and do those integrals. All right, so the integral on this is easy, so u2 has to be x here. It's easy enough. The integral on this again, and you may have just looked up the integral, but just to remind you on something like this. So let's say you see something like this. So I guess the reason I'm saying this is maybe you see this and you're like, wait, I don't know what that is. Even you can always break these things down according to what you know in pre-cal and kind of work your way back to the answer. So at some point in Cal 1 or Cal 2, somebody showed you what the integral of this is, and then say you're in this differential equations class and you forget. You still know that tangent is sine over cosine, right? So notice then that we can basically, you can integrate this using substitution. So, but again, it's just pre-cal, I'm just like, basically just trial and error, just poking. Well, sine over cosine. But now if this is sine over cosine, I know the derivative of cosine is negative sine. So essentially this top part is the derivative of the bottom. Sorry, we don't need the dx on the bottom. And that's perfect for substitution. So my substitution is that u is cosine. So I'm really integrating 1 over u du. The integral of cosine is negative sine, so all of that is just du. And what's the integral of 1 over u? That's going to be the natural log of u. So this is going to be the natural log cosine u1, it's going to be the natural log of cosine. Then once we have those, we can plug those straight into our form. We have our particular solution. So our particular solution then it's going to be u1 is going to be natural log cosine x plus x sine of x. And then just like before, that means our overall solution is yc plus yp is the complementary solution plus the particular solution. So our overall solution is b1 cosine x, c2 sine x, plus our particular solution, natural log of cosine x plus x sine of x. And again, what that means is we're now guaranteed that this part, so this part, the particular solution, when you take y double prime plus y, you get secant x. This part, the complementary part, when you take y double prime plus y, you get 0. So this gives you every possible function, which is constant, differences by constants, that when you do y double prime plus y, you get secant x plus, because 0 plus secant equals secant. That is our general solution. So especially for the problems that I've given you guys out of this, as far as your homework, which is pretty short, just gave you guys 3 problems. I mean, not just for those, but I mean, this is it. So this is variation of parameters. You can, so essentially, as long as you can form the Ronxian and then these W1 and W2, and remember that U1 prime is W1 over W, U2 prime is W2 over W, then you've got this. This is actually, so again, the particular solution, you have this different method and different assumption. But once you have that, the overall play is the same. That's your complementary solution, your particular solution, you slap them together, you got your overall solution. So, but also what I was trying to say is every problem then is like this. It's exactly like this. You just run this, you got your answer. Let me see. I gotta get to a lot of videos, not just for you guys, but for my other classes as well. So honestly, the thing is, every problem is exactly like this. So let me look really quick on, let me look really quick if we really need to see another problem, or if I can kind of let you guys run with this because this really is it. So give me a second. All right. I'm not sure. Maybe you don't need another one. Let's do one more go. We'll do number 11. Let's do one more go just to again just to get the procedure down, just to kind of play it through, so you can maybe see it, do it, make sure you got the feel for it, essentially. So let me write as we see here. So on 11, we're doing one. It's y double prime plus 3y prime plus 2y. So longer, kind of quadratic basically there. We have this 1 over 1 plus e to the x. Sure I got that right. Yes. So again, like I said, variation parameters, great for, or not just great, but really necessary when you end up with some funky thing like this. So this is not an e to the x, this is 1 over 1 plus e to the x. This is a quotient of functions. This is some weird thing that I definitely can't just say that YP is some generalized version of this, right? Because this is some weird combination of functions to begin with. So something like this, weird looking function on the right on your non-homogeneous equation, definitely going to use variation of parameter. Which means, again, the first thing you're going to do is find the complementary solution by going through the usual method for that. So again, what I'm gonna do is your auxiliary equation you come up with for this would end up being m squared plus 3m plus 2m equals 0, and then you would solve that, and that would give your complementary solution. So I'm gonna go ahead and give you guys a second to do that. So go ahead and pause on your side, I'll pause on my side, go ahead and solve that and get your complementary solution. All right, so easy enough. This factors into m. Sorry, and that wasn't even a 2m, that was just 2. That wrong. This factors into m plus 2 times m plus 1. Gives you m equals -2, m equals -1. Means my complementary solution is C1 e to the -2x plus C2 e to the -x. All right. Which means, so again, because this is some crazy function here, my yp, my guess on the particular solution is not going to be some general variation of it. It is going to be a variation of this complementary solution where instead of basically instead of a c1 in front of your e to the -2x, there's a function in front of it. So it's going to be u1x e to the -2x plus u2x to the -x. That's going to be my guess for a particular solution. And once I have this guess, then we go to forming the Wronxian W. Yeah, so the Wronxian, the W1, and the W2. So we first got to figure out those. But then we can get to forming U1 prime, U2 prime. But then you can integrate and get U1 and U2. All right, so let's kind of start those things in order. So if this is my complementary solution, then the first thing is, what is the Wronxian going to look like? So remember, the Wronxian is basically the first row is the parts to your complementary solution, and the second row is your derivatives. I actually want you guys to do that first. So we'll kind of do this with a lot of pauses, a lot of parts. So go ahead and pause on your side. I'll pause on my side. Go ahead and write the Wronxian out. Good. So easy enough. So the first row is e to the negative 2x, e to the negative x. And then the second row is the derivatives of these. So what was the derivative of e to the negative 2x? That's going to be negative 2 e to the negative 2x. What's the derivative of e to the negative x? It's negative e to the negative x. Good. And then you're going to take determinant of this. That gives you your w. Or we do that. Then your W1 is your Wronxian matrix, but your first column is replaced with 0 on top, and then whatever's your non-homogeneous part of your differential equation bottom. So we don't even have to pause for this. I'll just have you guys kind of shout at the screen. So what would W1 look like for this? Oh yeah, this differential equation. So again, it's going to be the first, you're going to take this first column and replace it with 0 on top. You're going to replace it with 1 over 1 plus e to the x on the bottom. You're going to keep e to the negative x, negative e to the negative x. So then how would you write W2? W2, now you're going to keep the first column of W, so it's going to be e to the negative 2x, negative 2 e to the negative 2x. But then on the second column, you're going to replace it with 0, and again, right side of our differential equation. 1 over plus e to the x. And then for each one of these, you're going to go ahead and do your determinant. Main diagonals multiplied, main diagonal multiplied minus backwards diagonal. That's the way I think of it. Main diagonal, backwards diagonal. Main diagonal multiplied minus backwards diagonal multiplied. Main diagonal multiplied minus backwards diagonal multiplied, etc. And that's going to give us our W or W1 and a W2, which is going to allow us again to form U1 prime and U2 prime. So let me see if I can have you guys work through this. There's a little bit of algebra there. So let me see if I can have you guys figure out your W, your W1, and your W2. So go ahead and pause on your side. I'll pause on my side. All right. So starting with W, and main diagonal multiplied. So e to the negative 2x times negative e to the negative x. So that's going to give me a negative. But what is e to the negative 2x times e to the negative x? Realize these are bases, these are exponents, exponential functions with the same base, so you're just going to add your exponents. What's negative 2x minus x? That's negative 3x. So this is going to be negative e to the negative 3x. And then minus backwards diagonal multiplied, e to the negative x times negative 2 e to the negative 2x. So minus, first of all, this is going to end up as a negative 2 in front, but minus a negative is plus, so this is going to be plus 2. And what's e to the negative x times e to the negative 2x? That is still e to the negative 3x. You have negative 1 e to the negative 3x plus 2 e to the negative 3x. We got like terms there. When you combine them, what do you get? It's 1 e to the negative 3x, or just e to the negative 3x. So that is W. And what about W1? So W1, we start with main diagonal multiplied 0 times this, but 0 times this is just 0. I'm not even gonna write that. And minus e to the negative x times this. Now, if you were working on the algebra for that, hopefully you realize that basically there's nothing you can really do to actually simplify that other than just multiply it. And so when you multiply it, the e to the negative x sort of ends up on top there. Yeah, I guess I think we'll write it that way. I'll go second. Oh, I'm sorry. So there is some algebra we can do it on it, and it will help us here. So, but I guess let me start there. So I think my first instinct would just be to write negative e to the negative x, or 1 plus e to the x. However, so e to the negative x really means you have e to the x multiplied on the bottom. So you can think of this as negative 1 over e to the x is 1 plus e to the x. And then now I can multiply that through. I want to do that. Did I get, maybe I got W wrong. Some issue that's gonna continue. There's just, I just the integration of this, I thought, that's okay. All right, well, we'll stick with that for the moment. That sounds good. Then for W2, we're gonna do the same thing. We're gonna do the determinant. We have main diagonal e to the negative 2x times this, which kind of write in a similar way. So we're gonna end up with 1 over e to the 2x times 1 plus e to the x, because e to the negative 2x just means 1 over e to the 2x anyways. So that's fine. Then minus 0 times this, but 0 times this is 0, so we end up there. Yes. So, all your Ronxian, your W1, your W2, figure out what those are. Now we're gonna figure out U1 prime and U2 prime, and U1 prime is still W1 over W. So in this case, it is what? Negative, so it's gonna be negative 1 over e to the x, 1 plus e to the x, and we are gonna divide that all by e to the negative 3x. And U2 prime is gonna be W2 over W, so that'll be 1 over e to the 2x plus e to the x all over, for W2 or whatever, yeah, all over e to the negative 3x. And this is where we have to do the work on some derivatives, but actually before we do that, there is a little more algebra we can do there just to simplify things, but that's. And so we're dividing by e to the negative 3x. So e to the negative 3x is 1 over e to the 3x, or e to the 3x on the bottom of the fraction. If you divide by it, it flips it back up to the top. So what we should see out of this is negative e to the 3x on top, e to the x over 1 plus e to the x on the bottom. And in a similar way on U2 prime, dividing by that is going to essentially going to put e to the 3x on top. So we're going to end up with the 3x, e to the 3x, e to the 3x over e to the 2x plus e to the x. And why is any of that important? Because now, again, I have exponential functions that are being divided. So I can simplify. This is going to simplify to e to the 2x. That's going to simplify to e to the x. So let's kind of reposition up here. So U1 prime is going to be negative e to the 2x over 1 plus e to the x plus e to the x, and then e2 prime be e to the x, 1 plus e to the x. And we put the x's in front of all that if we want. Then how do we find U1 and U2 from there? We integrate. Then fun. The rest of the job here, or your job from here is to integrate. And before I send you guys off on that, there's just one of these is an relatively easy integral. The other, make sure this works the way I think it should. Actually, back. Wait a second, I mean, this is likely fine, so you should be able to integrate this, but I feel like I got something wrong with you. Give me a second. Okay, all right, never mind, y'all. So this does work out. Stranger than I thought, but nonetheless, it works out. So then we have to take integrals, on both sides here. So let me go ahead and work through these integrals. I'm actually gonna work through U2 first. We'll need sort of the result from that to deal with U1. So, yeah, so these are just, well, this first one's gonna be substitution. You'll end up seeing as substitution. Second one, use that substitution sort of in a integration by parts. So this is just, again, this is a good review of a lot of your Cal 2 class. So this first one, what I do notice here, so I notice this sort of strange setup, but I do notice that the derivative of the bottom goes up in the top, right? So the derivative, if I made u 1 plus e to the x, du would be e to the x d to the x. So I'm gonna take I'm gonna make that or use that to my advantage. So I'm gonna call that u. And I know from there that du is gonna be e to the x dx. So if you make this substitution, then this reads as the integral of 1 over u du. Like we saw for tangent. So when you integrate this, u2 is gonna be the natural log of u, which is this 1 plus e to the x. So it's gonna be natural log of 1 plus e to the x. So easy enough on that one. Let's hold on to this. For U1, notice that the c to the 2x though is not, so unlike U2 prime, for U1 prime, the c to the 2x is not the derivative of e to the x. We don't sort of get that special treatment there, basically. And so if we don't have an immediate substitution we can use, so going back to Cal 2, you see this is basically, in some sense, this is two functions, either multiplied or divided. And that's your signal that this is likely going to be integration by parts. To do this integration by parts though, so it ends up, so let me just kind of show you kind of what you end up needing for this. Actually, based on this e to the 2x, I'm going to factor it as e to the x times now e to the x over 1 plus e to the x dx. Why would I do that? Notice that this now, the exact same integral we just worked. So in my integration by parts, I'm still doing integration by parts. So again, still realize that I have more than just this e to the x. So this piece is still here, still consequential. I'm still have one function times another. So this is still integration by parts, but what this allows me to do is this essentially is going to be my du that then creates that I can integrate up and create my u. So I literally can just take the result I got from this, and that's going to be my u in this case, this integration by parts. So u is going to be natural log of 1 plus e to the x. If that's my du, then this is my v. If this is v, what's my dv? We won't even pause. I'll just have you guys work that for a second. What is dv going to be? It'll be the same. It'll just be dv will be negative dx. Just negative e to the x. Oh, whatever. However this reads, yeah, I guess we will put the dx on there. All right, so I sort of factored off or pulled off this e to the x so that this piece would work for my du. This is honestly a problem like this. You're working on something on your own. The problem, the fun thing about integration with parts, the problem is you may make the wrong choice to begin with, as far as which is v and which is du. And so you might choose this to be u to begin with, the derivative, and then realize that that's not going to play out well for you using integration by parts. And the only way you're going to know that honestly is to try it, see that you don't like it. No, sorry, but try it and see that it doesn't work. So integration by parts, I tell my Cal 2 classes, by nature and trial by error thing. You're not gonna get so great at this that you can always see which piece is the V and which piece is the DU by some great intuition that you've developed over the years, right? So let it be trial and error. It's okay. So whatever try, one of them is V and one of them is DU, work it through and then see if it's playing out well. And if not, go back and switch them, see if it plays out better. Usually there's basically one way, almost always there's one way that plays out a lot easier and a lot better than the other way. Okay, so now let's start to put this together then. So then u1 is going to equal, so integration by parts says if I'm integrating v du, my result is u times v. That's going to be negative e to the x natural log of 1 plus e to the x minus the integral of v u minus the integral of u dv minus the integral of now negative e to the x dx u dv. Yeah, it's actually all in one line. Integral of negative e to the x natural log of 1 plus e to the x. Minus a minus is going to be giving a plus. That'll sort of nice. Now this then looks even worse to deal with. Surprisingly, this is going to be dealt with. So again, from your Cal 2 class, hopefully you have, even if you don't have it memorized, you kind of have something in your memory that says, oh, I can take the integral of a natural log. So it ends up with this part. You make this u, natural log of 1 plus e to the x. Then, well, actually, so if you make not just a second, how did this work out? Oh yeah, no, if you make make the 1 plus e to the x your u, then your du e to the x dx. And we can rewrite this then as, so I'm gonna make this plus the integral of u, sorry, u. Natural log of u du. So if I make this my u, du is gonna be e to the x dx, so this e to the x and the dx soak up that du, kind of, those are the pieces you need for it. Have natural log of the integral of natural log of du. And then we can actually take the integral of natural log. So it ends up with integral of natural log is plus u, natural log of u plus u. Hey, give me a second, let me do the derivative just to make sure that works. Minus, sorry, it's minus u, I believe. Yeah, it looks like it's minus u. It should be minus u. So, still, this is all, we got U2 figured out here. This is all U1. So now for U1, I'm gonna go ahead and replace, so I'm gonna replace this U that I put there and start working out the rest of this. And I think I'm gonna have to turn the camera. Still need to see the roots. So then U1 gonna equal negative e to the x. Natural log. One plus e to the x. Now it's gonna be plus, so my u is 1 plus, so plus 1 plus e to the x times natural log of 1 plus e to the x minus 1 minus e to the x is 1. Then we're gonna start distributing and simplifying. Plus e's correct. All right, so starting to simplify here. So I have negative x times that. That's nothing I can do there, but I can basically distribute this through here. So I end up with negative e to the x, natural log of 1 plus e to the x, plus natural log 1 plus e to the x, 1 times that, plus e to the x, natural log. Oh, there's something. The log of 1 plus e to the x. So these are just supposed to cancel. It's happening. Minus 1 minus e to the x. something here. I'm sorry, guys. So this is good. This wasn't supposed to take this long. Fuck. Need more time to do shit. Like I probably just missed something and then. Patient by parts. Good. That. I'm gonna need to get on to my second video for you guys anyways, so I'm just gonna figure this out right now, unfortunately. But at the least you can see these cancel. Shit is supposed to cancel with something else. But we're gonna end up with u1 equals natural log of 1 plus e to the x minus 1 minus e to the x after all of that. So then for yp, you stick 1 and u2 in front of their respective pieces, and then you tack it onto yc, and that gives you your overall solution. So, okay, you guys can write that out. I need to move on to y'all's next video. All right, but that's variation of parameters. So my point with that problem, which I probably should, you guys were good with the first problem. I probably didn't need to run a second, but my point with that is, again, every variation of parameters problems, you're gonna run the same. As long as really you can form those the Ronchian and those other pieces, and then do your integrals from form u1 prime, u2 prime, and do your integrals, then you've got this. So really quick, because I would feel weird if I didn't write the completion on this. So it'd be c1 e to the negative 2x plus c2 e to the negative x. And it would be, let's see, 1 plus natural log 1 plus e to the x. We're trying to do an enormous term here, minus 1 minus e to the x. This all is being multiplied by e to the negative 2x. E1, yeah. Then plus just natural log 1 plus e to the x, e to the negative x. That's going to be your overall solution. Okay, good stuff, but that's variation of parameters. You guys got that. We're going to use this actually a little bit in our next section, but our next section, we're going to generalize both, again, what you guys saw in 4.4, 4.3, and what you're seeing here. All right, I'll see you guys for that.